Total internal reflection then. When light passes into an optically less dense medium, part of the light is reflected as well as refracted. So we already know that most of it in a glass block is refracted. But we also should be aware that part of it is reflected. We see this whenever we perhaps walk past a shop window, and as well as seeing what's inside the shop window, we see a reflection of ourselves, a weak reflection of ourselves. So for this ray travelling through the glass, if we come to the normal, it is now coming out into the air, so it is bent away or refracted away, and there's a strong refracted ray, but some of the light is also reflected. So there's a weak reflected ray. And as we change the angle of incidence, the angle of refraction increases. In other words, this is the angle of refraction. So this is our angle of refraction, and as we change the angle of incidence, which is in here, the angle of refraction changes. Now I'm going to draw some diagrams which illustrate that in each of these examples as we gradually change them. Now, looking at these completed diagrams, the angle of incidence in the first one is very narrow, and we have a strong refracted ray and a weak reflected one. In the second diagram, the angle of incidence has increased, so the angle of refraction has increased. And we have a strong refracted ray with a bigger angle and a weak reflected ray. In this third diagram, we now have refracted the light so much that the ray of light runs along the edge of the block. The angle of refraction in this case is 90 degrees. And we have a strong ray of refraction running along the edge of that block with a weak reflected ray. What's interesting is that this angle is C, and C is the critical angle. The critical angle is the angle at which refraction is 90 degrees. If we increase the angle of incidence above the critical angle, we no longer have a refracted ray. All the light is reflected from the surface back into the block. So we have a strong reflected ray whenever we increase the angle of incidence above the critical angle. At the critical angle, we have this strong refraction at 90 degrees and a weak reflection, but at angles above the critical angle, we have a strong reflected ray. And we call this property total internal reflection. Total meaning all, internal meaning staying inside the glass, and reflection. So total internal reflection, all the light is reflected internally. The critical angle for glass, above which all the light will be totally internally reflected, is 42 degrees. So in this case, if we have a ray coming in, it's reflected. In this case, we're using a semicircular block. Some of it's refracted, some of it's reflected. So at 15 degrees, bearing in mind the critical angle for glass is 42 degrees. Do we have refraction or reflection in each of these examples? Well, if the angle of incidence is 15 degrees, we have refraction. You probably can't actually see this writing. We have refraction and reflection. That's 30 degrees. We're still below the critical angle, so we still have refraction and reflection. If the angle of incidence is 45 degrees, now it's greater than the critical angle, so we have reflection. At 60 degrees, we have total internal reflection. And at 75 degrees, we also have total internal reflection. So whenever we increase the angle I above 42 degrees, we have total internal reflection. This is sometimes called TIR. So, total internal reflection then. For a definition of it then, total internal reflection is when all the light ray is reflected at the boundary. And this occurs when the angle of incidence is greater than the critical angle for that material. Depending on whether it's glass, perspex or water, the critical angle will be different. So, total internal reflection, a definition of it again, is when all the light ray is reflected at the boundary. And this occurs when the angle of incidence is greater than the critical angle for the medium. The uses of total internal reflection. Well, we have totally reflecting prisms. For example, if we have a 45-degree triangular prism, if we have light coming in that meets the glass at 45 degrees, so if this is the incident ray meeting the glass at 45 degrees, it will be reflected at 45 degrees, which of course then gives us an opportunity to change the direction of the light by 90 degrees in total. This prism is used, prisms are often used in periscopes now instead of mirrors. They can put in the glass or perspex prism and then refract the light instead of using mirrors. Also, in a different way, it's used in binoculars to reflect light through 180 degrees. In this case, the light is coming in from this direction, meeting this surface, being reflected by this surface, then meeting the second surface and being reflected again, and then returning out through the initial one. So if the light comes in the normal of the hypotenuse, if you like, of the triangle, it's then reflected, and a parallel ray returns back out. So it's turned round 180 degrees. It's also used to a great extent in optical fibres. If the incident ray meets the inside edge of the optical fibre at an angle greater than, an angle of incidence greater than 42 degrees, it can be totally internally reflected. And this is the case even if we bend the fibre in any direction. These are used extensively in medicine as an endoscope to look at organs inside the body. And they're also used in communications. Now, a bundle of optical fibres can send a light ray carrying data through the optical fibre. Dispersion is the next property we want to look at. Dispersion is basically whenever we have a ray of light entering a prism, for example, a triangular prism here. So this is a white light ray. It can split the white light into the different colours, and this property is known as dispersion. The different colours of light have different wavelengths, and they are refracted then by different amounts. Whenever the white light meets the surface, each of the different colours are refracted by a different amount. The red light is refracted least because it has the longest wavelength, and the violet light is refracted most. And we call this range of colours spectrum of visible light. So this is the spectrum of colours of visible light. And you should learn the order of those colours. I'm sure that you've learnt them already. Red, orange, yellow, green, blue, indigo, violet. And rainbows actually illustrate dispersion very well. And this dispersion occurs